So this is the last topic of our applications of derivatives unit. We are going to be having a test next week, Friday, on applications of derivatives. So I can put that up on the board here. So Monday is a holiday. Monday there's no class. It doesn't count as a day. So next week we'll have class on Wednesday and Friday, and we will have our test on applications on the Friday. Yes. So what we're going to do for optimization problems is these are word problems where you want to find a maximum or a minimum. What is the maximum area of a fence? Do you remember these questions where you put a fence along a river, farmer wants to keep his grasshoppers in a fence or something like that, and you had a certain amount of fence and you wanted, you wanted to find the maximum area? Well, now we can use calculus to do this so much faster than we used to do it with quadratics. So we did these kind of questions a little bit already in grade 11 math with quadratics. Now we're going to be able to do them faster with calculus. So what's going to happen? We're going to draw a diagram and look at our sketch and try to make an equation with whatever we want to optimize. So for that area question, you're going to want to make an equation that's area equals. And then you want to make sure that you're using only one variable. We find the derivative of whatever we want to find the maximum or minimum of, and then look at the values you get. Make sure that they're reasonable in the context of your problem. So here's a first example. This one, the equation's given to you. So no sketch is going to be needed. A ball is thrown vertically upwards at time t seconds after the initial projection. Its height is given by that formula. According to this formula, if you would do the second derivative of this formula, you would get -2. So this is on some planet with a gravity of -2. Does it say meters per, is it second? Yeah, meters per second. So we're on some planet where the gravity is -2 meters per second. Wonderful. And we want to figure out the time at which the ball is at its maximum height and the value of y at that time. Well, we've got a parabola. Can you see that that's a parabola that's opening down? And if you found the derivative of that and set it equal to 0, you would find the time, 7.5 seconds, where this reaches its maximum. And then if you plug that value into the original equation, you can find the height that it was. Now these are going to be the most easy questions where you want to find a maximum or a minimum and the equation is already given to you. Really, there's no amount of work that needs to be done other than taking the derivative, finding that value, and then stating the maximum. For our second example here, this one is just like the ones we used to do in grade 11. We've got a rectangular parking lot you want to enclose with 60 meters of fencing to keep in those grasshoppers. Okay? There's a building on one side, so no fence is required. Find the maximum area that Fred can enclose. So the same way you would have done this question in grade 11, you would have drawn a little diagram. And we've got two sides that are going to be the same and one side that's going to be different. So we can start by labeling it with two variables, and you find out that 2x plus y has to equal 60 because you have 60 meters of fencing in total. But then what you're going to want to do, we want to find the maximum area. So we're going to want to write area equals. Now if we look at our diagram, can you see that area equals x times y? But we're going to want to make our equation using one variable. So instead of x times y, can you see that we've solved for y here? It's 60 minus 2x. So we can write our equation as our area is going to equal x times 60 minus 2x. That's going to be key in all of these optimization problems. We're going to want to write an equation that only uses one variable. Because once we do that, now to find the maximum or the minimum, we take the derivative. Taking the derivative in this case and setting it equal to 0 tells us that x has to be 15. And if you look at the mathematics, how hard was it to find x equals 15? Really quite easy. Is that a lot easier than our completing the square technique that we used in grade 11? No, you think this is more difficult? Or they're both the same? I think this is quicker. I think that this is quicker than the completing the square technique that you learned back in grade 11. Because all you have to do, the completing the square, you would have still had to create the equation just like you did up to here. And then the derivative and setting it equal to 0. And then once you've got x is 15, well then you can find your maximum area by plugging 15 back into your original equation. And you've got an area of 450 meters squared. I want you to read this question, and I want you to just draw the diagram of what's happening. This is a calculator question. So I want you to draw the diagram, and then even after you've drawn the diagram, we want to find the maximum volume. So that means you're going to want to make an equation with volume. So see if you can come up with the equation as well. So picture for this. This is a 10. And then you cut out corners, and those would be folded up. Once it's folded up, your height will be x, your width will be 10 minus 2x, and your length will be 7 minus 2x. Multiplying that all out, we get an equation for volume. Now, you would have to do at least this part without your calculator. But this is a calculator question. So two ways that you could go from here to find that maximum volume. One way is to take your derivative. If you take your derivative and set it equal to 0, you could use your calculator to find out when it's equal to 0, and you find out that it's at 1.35. So what I did is I took my derivative, I set my derivative equal to 0, and then graphed it on my graphing calculator and found out where it was equal to 0. Now there's two values on your graphing calculator where it's equal to 0. There's also another one right here. The problem with that value, I believe that that one is just a little bit more than 4. Can you see why that one that's a little bit more than 4 does not make sense with our diagram? If you cut out squares that are more than 4, what's going to happen to your side that had 7? There's going to be nothing left. so it doesn't make sense. So the only answer that does make sense is the 1.35. So in these optimization problems, often you'll get a couple of answers and you're going to have to think about which ones make sense. Once you've got that 1.35, you could find out what the value is. Now, since the value that we have here is something you need to use your calculator for, what's another way you could have found your maximum? Your value for x that would give you your maximum. You could have just graphed the original function and then used your calculator to find the maximum. And on your second part of your exam, there will be questions like this. You have to think, what would be the fastest way for me to, if I have my calculator, once I've got my equation, which we had up here, right? There's your volume equation. You could just type that in and find your maximum. Again, we look at our graph and it does go up forever. So someone might argue, well, maybe there is no maximum. But again, we have to think about any time that you are getting bigger than 3.5, anytime your x values are getting bigger than 3.5, look at our diagram. That doesn't make sense anymore, because then you've lost a whole side of your box. And when you fold that up, it doesn't make any sense. So the only part of this graph that actually makes sense is this section here, and there's your maximum. Yes? Yeah, and we've done these last year, right? And last year we got the equation and then went to our graphing calculator to find it. And if it was a calculator question, you're fine on doing that again. It may be, however, that this question comes up on a non-calculator, and they design the dimensions so that it works out perfectly to a nice number. In that case, you wouldn't be able to use your calculator. Then you would find your derivative, and chances are this would factor nicely. Obviously, with an answer of 1.35, it doesn't factor nicely. Or they could give you something that doesn't factor nicely on a non-calculator part and expect you to use the quadratic formula to find x. That could happen as well. But then they wouldn't ask you to find y, because plugging that in would be too much calculations to make. So there are both ways using your graphing calculator. One, finding the x using your derivative and setting your derivative equal to 0. Other, finding your x by using your actual maximum of your original function. Both of them give you a volume of 42.4 centimeters cubed from your calculator. So here's a triangle. You can adjust that triangle any way that you'd like, just as long as x plus y is always 6. So can you imagine moving that triangle around? You get different sizes. If you wanted to find the maximum area of that triangle, you would need to write an equation, area equals, and try to do that using only one variable. So only x. I'm going to give you a little moment to try to think about that, see if you can write that equation for that area, and then we'll go through this. So y is equal to, well, if the two add up to 6, then this y is going to equal 6 minus x. And then when you set up your area of a triangle is base times height divided by 2. Now we can write the base as 6 minus x, the height as x. Multiply that out, and we get 1/2 x squared plus 3x. Again, you could complete the square with that, but you're going to have a lot of fractions to work with. Or we can just take the derivative, set the derivative equal to 0, and find out when x is equal to 3, you have your biggest area. And that area will be 3 times 3 divided by 2, or 4.5 centimeters squared. So again, look at the next question, find out what you want to optimize, and see if you can write an equation for that. So here's our next question. We want to find the sum so that it's a minimum. So we want to optimize the sum to be a minimum. And so that's what you need to make an equation for. Sum equals blah, 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 blah. And in that blah, 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 you need to have that in terms of x only. So I have two numbers. I have an x and a y. But I need to relate them in terms of x only. See what you come up with. All right. So first of all, the two numbers multiply to 48, so you can get y in terms of x. Y is going to be 48 over x. Then setting up your equation for your sum, your one number plus 3 times 48 is 144 over x is equal to your sum. That is your equation. So when you find the derivative of that, okay, I would probably write the 100, and I might take an extra step here and say it's x plus 144x to the minus 1, because that will make my derivative a lot easier to do. The derivative of x is 1, and then I bring power rule, bring the negative out in front, subtract 1 from the exponent will give me an x to the minus 2. I've now rewritten that with that x squared on the bottom. Get a common denominator, write that as a final fraction, there we have our derivative. If we set our derivative equal to 0, well, a fraction is equal to 0 only when the numerator is equal to 0. So you can either just set your numerator equal to 0 like I've done here, or you can show an extra step where you multiply both sides by x squared to get rid of the fraction, and 0 times x squared is still 0. So it does the same thing as create x squared minus 144 equal to 0. You get two answers then, plus 12 or negative 12. But the question told us that they were positive numbers to begin with. So the only possibility for x is 12. That means your value for y has to be 4. Mm-hmm. Okay. Yes. And it doesn't matter if you had written it the other way, then you would have got x to be 4 and solved for y to be 12. And that would work out fine as well. So if you had done it the other way, can you see that your equation would have been this? 48 over x plus 3x equals your sum. Is that what you set up? And that, doing that same derivative that way will give you the same answers. Guess I kind of gave it away with the picture here. So does that picture look reasonable? We've got an open box with a square base having a total surface area of 192. So I will know that the dimensions on the bottom would all be x. My height could be a different number, so I labeled that as y. So we want to make a volume that's a maximum. How do we write an equation for volume that only has one variable? Well, there's always going to be something else in the question that allows you to relate the variables. And I think in all of the previous ones that we've done, that relation has been really simple. Oh, the two numbers add to 6. Well, that was not very hard to create an equation. But this one is harder because it tells us the total surface area, and we're going to just call it an outside surface area. Should be clearer in this one because I guess technically you could count the inside of the surface area as well, and then that will be much more difficult to do. So we're going to add the word outside there. Our surface area, can you see that our surface area is going to be the bottom, which is an x squared, plus there's 4 sides that are each x times y. And that's 192. So if you want to solve for y, make my y's look a little bit less like 4's here. You'd have to subtract the x squared and divide by the 4x. And that'll give you an equation for y. Now how do you find volume of a rectangular prism? Length times width times height. So now we can set up our volume equation. I notice that I have an x on the top and an x on the bottom. So from this step to this step, all I did was simplify one of those x's. From this step to this step, I multiplied out the top, and then I divided each of them separately by 4, because then this would be in a form that I could just use my power rules when I differentiate. I mean, I could have left it as the line before and used quotient rule or product rule, but I felt it would be easiest if I got it into the form, so I just had to use my power rule to find the derivative. Now that it's in that form, I can take my derivative and set it equal to 0. Of course, you get plus or minus 8. You're talking about dimensions here, so only positive 8 makes sense. And when we plug in 8 into our formula for y, we get that y has to be 4. And now we know our dimensions have to be 8 by 8 by 4 in order to have that surface area, but to get the biggest volume possible.